Okay, so in our lab, we looked at some geometric figures that we can get from our undefined terms, point, line, and plane. What we found is especially a line, when we take a line and we intersect that line, we break that line up, we can get different parts. I'm going to start with a ray. Ray was the first thing we formed. A ray is half of a line. I'm put that in quotes. It's still this, it's the same size, but we've taken half the line. It's half a line, has one endpoint. And it goes infinitely in one direction. So if we were to draw a model of a line, one might look like this. I could have an endpoint A, I'm going to label that EP, and I can have a second point that helps me know, well, which direction is this ray traveling in? And maybe that'll be point C. Okay, now how do we label a ray? Lines were very flexible. We could label a line AC or CA. It didn't matter because they traveled in both directions. Rays, it's very important the order. Order matters on this one. We always have to start with the end point and then do the second point. And then we label it with a one arrowed line, a ray, above those two letters. So for instance, in this example, we might have ray A, C. Or it might more realistically look like this. AC with a ray over it. Ray AC. There's a whole language to geometry, syntax, punctuation that we're learning. Okay. Whereas if I had, say, this ray, okay, I drew my points looking essentially the same, but if I have C be my end point and A my second point, this is ray CA. I always do my end point first for a ray. Any questions about rays? And the labeling thereof? Okay, so then we took a ray, we cut off part of it. So we started with the line, cut that in half, now we have half a line, then we cut another piece off, and then we had a segment, a line segment, or we'll refer to these as segments. E, G. Okay, so a segment is a piece of a line with two endpoints. It is not infinite, it is defined, it is measurable. We can't measure the length of a ray, it's infinite. We could run our ruler along it, but we don't have a ruler long enough to get its full measure. Same thing with a line. But a segment we can measure, okay? And we label segments with the two endpoints. The order doesn't matter, similar with a line, and a segment on top. So that's how we know this is a segment. It's not a line, it's not a ray, it's a segment. So we have three figures that we can name with two letters because they're defined by 2 points. We have a line, which goes infinitely in each direction, arrow on both sides. We have a segment, which is not infinite at all, just has a little segment drawn above it for the 2 points. And then we have a ray, which goes infinitely in one direction, so the order of the letters is important because the ray goes in just one direction, and we need to know which direction that is, okay? So these three things are defined by 2 lines. Any questions about segments? Now we're going to refer to these as segments from now on in geometry, so we don't confuse them with a line, okay? All right, and then when we took two rays and put them together, so for instance, I could take a ray AC. We always need a second point to our ray to know which direction it's going. We can't name a ray with only one point. We always have to have 2 points, an endpoint and a second point. And if I add a second ray, say ray AB, then I have an angle. Okay, an angle is just two rays with a shared endpoint, or a common is another term you'll hear, endpoint. Okay. This angle is made up of ray AC and ray AB, and the common endpoint is A. When we name an angle, this is our first two-dimensional figure. Everything else was one-dimensional. We could label it with 2 points. Now we have a two-dimensional figure. To label it, we need 3 points. So we need one more point than dimensions, right? So our array is 2 points. We have some flexibility here, but we start it with this little angle indicator at the front, and then we use 3 points on the ray, on the angle. This center point must always be the common or shared endpoint. It has to be the vertex. Shared endpoint, also known as the vertex. Okay, so this would have to have A in the middle. Beyond that, I can do the other 2 letters in either order. I could have cab or back. So there are 2 different ways to name this particular angle. But that letter in the center, if anything else is there, would be wrong. You have to have the vertex, that common endpoint of the rays, in the center of the named angle. Any questions about that? Angles? Okay. This is brief. We have intersecting lines. We touched on this briefly. Any 2 lines intersect in a point. So any 2 lines that intersect any point. One point. Okay, we're not going to, we don't label this in any particular way. We label points with a single capital letter. But for instance, if I have this line, CB, and I intersect that or cross it with this line, AD, they will intersect at a point. Even if the point isn't listed, even if it's not labeled, there is a point there. I can label it. I could choose to label it O, or any letter that's not being used in the diagram. Okay, so that's my intersection point. And then what about parallel lines? What do you know about parallel lines? Lines are next to each other. They go infinitely but never touch. All right, so parallel lines never intersect. Okay, and they could be next to each other. They could be very far apart. For instance, assuming the ceiling has been done correctly, the top of this wall and the top of that wall, if we continued them forever, even though they're a building apart, they would go on forever without ever touching. But they are the same distance apart. Ideally, I'd measure from this wall to this wall, get the same distance as if I measure from that wall to that wall, right? So parallel lines are always the same distance apart from each other. Okay, now we do have a special way for indicating that lines are parallel. If I just draw 2 lines that look parallel, right now we'll just say, yeah, those look parallel, they're probably parallel. But at a certain point, I'm going to say, okay, guys, now, unless we know for sure they're parallel, we can't assume they are just because they look like it, okay? So either we'll be told lines are parallel, or in a diagram, we'll have an extra set of arrows in the middle of the lines. That means those two lines are parallel. That's our visual indicator. Okay. And you could put this in that box just as well. All right, any questions about parallel lines or intersecting lines? All right, we're going to pick up with radicals in a moment. You may have simplified radicals in a previous algebra class. A lot of you I had for algebra, but some of you I did not. Devices closed, please. Pencils out, notes. Closed. Thank you. Notes. All right, this is the fastest possible way to simplify radicals. Okay, so that's what I'm going to teach you. I'm going to adjust this question here, add a 2 in front. We're going to make this 2 radical 80. And to simplify radicals properly, we need to know our perfect squares. So I'm going to write it this way. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Square root of 16 is 4. Write these down, please. Anything I write on my notes page, you should write on your notes page unless I say otherwise. Wow, I just went 64 is 8, 81 is 9, is 10, square root of 121 is 11, and square root of 144 equals 12. All right, so these are our perfect square facts, the square root of each of these numbers and their values. This is going to help us quickly simplify a radical. So we have this procedure, and I started doing my notes like this with the procedures on the right and the example on the left, so that when you're working a separate problem, maybe with your IXL notebook, you can set your IXL notebook right here and follow the procedure for a similar question, okay? So we have this 2 radical 80. We're going to start by finding the largest perfect square factor of the radicand, what's inside the radical. So I'm going to keep this 2 on the outside there. I have this radical 80. First of all, is 80 a perfect square? Yeah. No, 81 is, but 80 is not. Okay, then I'm going through the factors. So 80 divided by 2 is 40. That's my next largest factor. Is 40 a perfect square? No, okay. Then let's go down from there. 40. Is 36 a factor of 80? No. Is 25 a factor of 80? Is 16 a factor of 80? It is. 16 shows up kind of a medium often. So 16 is the factor of 80 that we're going to use. If you need to carry on that conversation, take it outside. Joshua, if you need that conversation right now, do it outside. Otherwise, mathing. All right, so 16 is a factor of 80. So I'm going to rewrite 80 as its perfect square factor. I'm going to put the perfect square first. And then the other thing I'd multiply times 16 to make 80, which is 5. And I can use my calculator, 80 divided by 36, 80 divided by 25, 80 divided by 16. Boom, 5. Okay, then I rewrite this as the root of the perfect square and the root of the remaining factor. So 2 radical 16 times radical 5. This is a property of algebra we studied, I want to say in chapter 7, maybe chapter 7. All right, then I can simplify this perfect square factor. My square of 16 equals 4. I still have this 2 and this radical 5. And then if I have any additional numbers in the front, I simplify them by multiplying them together. 2 times 4 is 8. Okay, that's the fastest way and the simplest way to factor. It's a nice set procedure you can follow. On the formative lesson 1.1,